I'd like to talk about an interesting two-transistor configuration. And basically it's a case where I've got two nFETs, they're stacked on top of each other. They both have two various components to it. They both have source and drain terminals. There's a common source and drain terminal tied between the two of them. There's a lot of different things you can think about here. And then you have two gate terminals, one each, that are fixed. These are going to be parameters in the discussion we're going to be building. And so basically I want to look at results of voltage versus current in these structures. And you think, okay, what would I probably be looking at? Well, if we look at V versus I, where basically looks like a typical drain type of curve. Where again, notice that the lowest terminal is sitting at ground. And so you'd expect to get these sort of ohmic and saturated regions. And kind of curious what kind of pieces you get. Well, the first thing you might ask is, well, what are those boundaries for dealing with between subthreshold and above? Well, subthreshold is what we're going to work with here, but now we're going to talk about between saturation and ohmic. Okay. And by the way, the same reasoning would go in above threshold, but it's a little more complicated. But let's at least talk through this. What I would need to have is between the two source drain terminals for the transistor that has V bias is I'd need to have V be greater than V1 by 100 millivolts. I would then, for the one that has Vref as the gate voltage, that one would have to have V1 greater than ground by 100 millivolts. And you think, great, all I'd really need is 200 millivolts, and that's probably not too challenging to come up with to get something in saturation, and then you get an ohmic regime. Great, this works really, really well. No problems whatsoever, right? But this kind of makes an interesting assumption for that to happen. For it to be 200 millivolts, it means that V1 must be set exactly at 100 millivolts. It means I would need to set V bias to be exactly in that place. And that's an interesting sort of physics question here when you look at the circuit. And some of you might look at this and go, oh, does this have to do with certain optimal biasing for cascode circuits? Because often you use this configuration to build cascodes, and this is in fact exactly one of the questions you might ask. Okay, so to do that you might say, well, how do I figure out V1? And there's a couple different ways to do that, but sort of a general way to look at that approach is it's going to be sort of kappa times the difference between V bias and Vref. And V bias and Vref operate sort of in opposite polarities there. We're assuming the same kappa for the two ends, which is more or less reasonable, although there's some subtle shifts that happen with bias, so be aware of that. We're also, again, assuming sigma is much, much less than 1, and that's going to be helpful because you can start by writing the equations in ohmic for the two transistors here and here. And it's not just ohmic, but it would be true for both, right? Both saturation and ohmic regime. But then you can also say, what is the simplification for saturation, which means this term over here basically approaches 0. All right, not too bad at this point. So when you take a look at these two equations, and if you kind of just start off by assuming sigma equals 0, you immediately can derive out that this is your relationship for what V1 would be as a function of V bias and Vref. And you think, oh, that gives me an idea of where to roughly be putting that. Now when we look at the circuit, we're going to typically assume V bias is greater than Vref because that's typically how you can operate it. Otherwise, it's really the V bias transistor is constraining the rest of the system, and Vref will do something different. So be aware that that's the way I want to think about it. It's kind of fun to kind of flip that around though, and that's a really interesting kind of mental exercise to kind of think about here. Well, if you're in subthreshold and saturation, it turns out if you solve these two cases more carefully, you get this equation between V1 and sigma with the other terms, and it does get interesting because you do see again this difference term, but more specifically you notice something else, is that V1 changes with sigma V, but it's like for a change in V I get a sigma V change in V1. So large change in V becomes a really small change in V1, and you think, well, that's kind of an interesting idea. So it means that this can move a lot and this doesn't move much at all. That might have some impact on the overall physics of this. And that's something that we can kind of look at. So How does that look? Well, take a look at two different cases. One where the difference gives you about 700 millivolts, and one where you get it at about 100 millivolts. And notice the different trajectories you get here. When you start off initially in the first sort of 100, 200 millivolts, this rises up at a very typical structure that you would expect primarily being dominated by this transistor. This transistor looks like it's just basically a conductance that everything's just passing through. So you get up to this point, and what happens? Well, then it looks like it hits a saturation regime. And look, it basically follows whatever the sigma. And the sigma we're using here is 0.05. It's kind of a large sigma, but I wanted to use that to illustrate a point. Not out of a realm of certain sort of very deep submicron devices, so don't be surprised if that's a number you might see in some places. And so you definitely can see, here you can definitely see there's a change there. Up until you get to about that 700 millivolts plus 100. And then you go, wait a minute, this gets really flat. And how flat? Well, if you think about it, it's sort of double sigma flat. Because V1 gets very small. And you can basically sort of put that into this term. And what you realize now is it's like a sigma squared in that sort of early effect channel length modulation Dibble term. And this is one of the things that people often like to do with this circuit, is to get a really flat structure here. And you can see it's really quite flat in this space. What you do see as well is that if I were to start this at 100 millivolts, it looks like it goes all the way up to the 200 millivolt point and then just straight flat. And this would be like a really good spot. Why would I want to do something to make it really flat? Well, remember that often I want to use transistors as current sources or voltage-controlled current sources. Well, the more flat it is here, the more close to an ideal current source it is. And so this is a case that you see when you do this with Cascode structures. Now you can do a similar thing for above threshold. It's kind of an interesting structure, but now you got the quadratic. You don't get the sigma embedded quite as nicely. There is a sigma, but you also have an early voltage due to some of the channel length modulation. They change in terms of the way they're approaching it. So it's a little bit messier math, but at least in terms of the overall crossover point, you still see the exact same relationship you see here. You'd see the same dynamic, same behavior in these two cases, except that this is probably not going to be quite as flat. This will be not quite as good an approximation just because this quadratic term and its resulting transconductance doesn't behave quite as well. But otherwise, this is a really, really good technique, an extremely good technique to be able to get a more ideal current source with basically very, very little cost, assuming you put various biases and techniques in the right place to sort of give you as much headroom as possible.